we're going to be considering Faraday's law, DC generators under this course, and we'll start generally with Faraday's law of induction. To begin, the electric fields and magnetic fields we study under electrostatics and electrodynamics are produced by stationary and moving charges respectively. When electric field is applied to a conductor, current is produced, which in turn generates a magnetic field. One could rightly ask whether or not an electric field could be produced by a magnetic field. Michael Faraday's discovery of 1831 shows that by varying magnetic field with time, an electric field could be generated. The phenomena is known as electromagnetic induction. The figure below, figure 1.1, illustrates what I just spoke about, which is Faraday's experiment. We can see here that a galvanometer with a coil of wire, when the magnet with the north pole pointing towards the core of wire is brought in, there is a deflection in the galvanometer towards the right. In the second pallet, the magnet is held stationary with respect to the wire loop, and there is no deflection in the galvanometer. In the third, the magnet is moved away from the loop, and there is a deflection in the galvanometer but in the opposite direction. So Faraday's experiment shows that no current is registered in the galvanometer when the bar magnet is stationary with respect to the loop. However, a current is induced in the loop when a relative motion exists between the bar magnet and the loop. In particular, the galvanometer deflects in one direction as the magnet is moved towards the loop, and the opposite direction as it moves away. Faraday's experiment demonstrates that an electric current is induced in a loop by changing the magnetic field. The coil behaves as if it were connected to an EMF source. Experimentally, it is found that the induced EMF depends on the rate of change of magnetic flux through the coil. Now let's talk about magnetic flux. Consider a uniform magnetic field passing through a surface S as shown in this figure, figure 1.2. We can see the area vector A, which is equals to the magnitude of A and the unit normal N, and the magnetic field B with an angle between the area vector and the magnetic field theta. The surface is S. The magnetic flux through the surface is given by phi B is equals to vector B dot vector A, taking the magnitude yields BA cos theta, where theta is the angle between B, the magnetic field, and the unit normal N. If the field is not uniform, thus if the field varies, changes, then phi B becomes the double integral, surface integral B dA. The SI unit of magnetic flux, we already explained, is Tesla per meter square. That's SI unit of, it's called a Weber. Faraday's law of induction may be stated as follows. The induced EMF E, that's epsilon, in a coil is proportional to the negative of the rate of change of magnetic flux. That's E is equal to the negative of the rate of change of magnetic flux. For a coil that consists of n loops, the total induced EMF will be n times as large. Thus, the EMF is now minus n change in flux with respect to time. That's equation 1.4. When we combine equation 1.3 and 1.1, we obtain for a spatially uniform field B, epsilon is equals to minus delta B delta T AB cos theta differentiating this function with respect to time gives us the quantity on the right, which is equation 5. Thus, we see that an EMF may be induced in